Same plan as what we've been doing. Do 30 minutes or so of test 3 stuff. Whether you want to talk about homework questions or just keep on picking away at this stuff or whatever you guys feel like you need to do, we'll do that for a half hour or so and we'll transition over to 3.9.
I have a question. For the 310 homework,
Yes.
I was trying to find the notes on it, and when I clicked on 310, there was no notes. So, did we do any notes on it that you want to remind me of?
So the 310, the whole idea is just like you make a tangent line
Okay.
and then use the tangent line to approximate the function.
Okay.
That's the entire idea.
Okay.
And like the books, some of the notation is really wonky and like difficult to use. So just try to try to stay out of it this year because it feels like it's more work than it's worth.
So, 310 homework, do you still want me to do it?
Sure, but if you'd like, if it's like a problem, then like whatever, you know.
Okay. Because I submitted my 7,
Yes.
and I didn't submit the 310 because I couldn't find the notes on it.
Okay. But like, you know, if it's semi or something, just do this. You know, that's something cool. Okay. What do you guys want to start with here as far as test review stuffs? You got some homework questions, okay?
I like the ending questions.
Yeah, we can do some more of that stuff. While Brooks is looking, let's do a couple of these things and we can circle back. Sound good?
Yeah.
All right. Did we do this last time? What did I do here? This is the 8th hour notebook. Did I do first hours in the wrong notebook or something? Do we not do this problem in here? No, okay. Well, here's what we're gonna do. Let's even it out in like the dumbest way possible. We'll do it here in the first hour notebook, and then they'll have it, and it kind of evens it out, right? All right, this says consider the curve defined by negative 8x squared plus 5xy plus y cubed equals negative 149. And the first part is asking us to find the derivative. What do we do with that? Okay. And then product rule, good. So what do we get when we do the derivative of 5xy with the product rule? 5x dy dx, good. Plus 5y, excellent. Good, 3y squared dy dx equals 2. Great. And then we add over the 16x and subtract over the 5y and then divide over the 5x plus 3y squared, right? I'm just going to do that algebra in one step. Does anybody object to that? Right, at this point when the calculus is done, the algebra is fairly straightforward. Feel good? Okay. Part B says write an equation for the line tangent to the curve at the point 4, -1. So to write the equation for a line, I need 2 things. Point and a slope would be the other thing. Finding a second point on the line that we don't know where it is going to be rough. But point and a slope we can do. So the point is obviously, given to us. How are we going to find the slope? What's that?
All right, time's up.
Yeah, we plug that into the derivative, right? The slope is just the derivative evaluated when x is 4 and y is -1. So 69 over 23 is 3, I think. Equation for line.
Do we have to go back to your work when you see it?
If it doesn't ask it for a specific form, it's an equation for line, it's an equation for line, whether you want to get the slope or slope intercept or standard form or some other weird convoluted way of writing it. Correct is correct is correct. The directions don't specify. A line is a line is a line. Any equation for line will do. How's that sound? Good. I thought so too. C says there is a number k so that the point 4.2 comma k is on the curve. Using the tangent line found in part B, approximate the value of k. How am I going to do that? Yeah. Well, or just put the k as y, right? Oops. And I just subtracted the 1 over. So what is that? 0.2 times 3 is 0.6 minus 1 is 0.4. Oh yeah, negative 0.4. Good. Nice jobs. Paying attention. Does that feel okay? No big deal there. D says write an equation that can be solved to find the actual value of k such that 4.2 comma k is on the curve. How do I do that?
Is this test 3 MCQs and network uses tabulator?
Yeah. Except I'm on first hours because apparently I wrote the answers when I did first hours into 8th hours, and now we're writing 8th hours into first hours, but it's the same work either place. Sometimes you do dumb things. You ever do dumb things? Happens to me all the time. What do you guys think though? How am I going to find this? How am I going to write an equation to find the value for this k if the k is on the curve? The actual value of k, not the approximate. Nope. Yeah, right? A point on the curve has to satisfy this equation, right? That's good. And again, if you want, you can clean that up. It doesn't ask you to do anything more than give you an equation. I wouldn't clean it up past that. Is everybody okay? And then E says to solve the equation in part D. What kind of an equation do we have there in part D? Some vocabulary review for you back. It's a cubic trinomial. Good. Between the two of you, got it. What else do you notice about this cubic trinomial that's particularly going to be a problem for us? Well, k is in 2 different places, and we have a constant term, right? So if it's cubic with 4 terms, maybe we have a shot at factoring that. We could try grouping on it. Cubic with 3 terms, where one of them's the constant, so there's like no greatest common factor or anything. Do any of you guys have any idea how to factor something like that? I don't either. There's not a good method for it. What do? Well, that's not going to help us to factor out a k because there's not a k in all the terms.
Could you do the -8 4.2 squared, move that to the right, to get that, and then factor out the k with that?
Well, you can do that, but what are you going to do then? What is that? That doesn't get us anywhere because it's the factored form isn't equal to 0, so you can't zero product property it, right? You just how many numbers multiply to give you -149 plus 8 times 4.2 squared? I'll tell you how many. Infinitely many, which is rough. You got one hope. Calculator is what you need, yes. How would you solve this on a calculator? Graph it, yes. You could graph it one of two ways. You could graph the left-hand side, the right-hand side, look for the intersection. Or you can move everything onto one side and then find the x-intercept. That's the way I would go, because it'll be easier to find the x-intercept because you know you're looking where y is equal to 0, so you don't have to like hunt for the intersection quite as bad.
Didn't we do that in step D though? Wasn't that what that was trying to find k? Or
Yeah, we're step D, we're just asked us to write the equation. In this step E, it actually asks us to solve it. All right, so what do we have here? We have, okay, so we have -8 times 4.2 squared plus 5 times 4.2 times x plus, what's that? Oh, it should be no 3 there, it should just be k cubed. Nah, that's not what I wanted. That's plus x cubed, and then I'm going to add the 149 over. Oops. But not in the exponent.
that would be
Yeah, it would be a big problem, right?
or it would be negative really small.
Is everybody okay here with what I did?
Yeah.
I'm just going to do like a zoom standard because, well, I know that for -1 is a point on the curve. I'm guessing 4.2 is going to be relatively close to -1. I don't know that, but like I think that's a fair guess. So I'm just going to do like a zoom standard here to just get my normal window. I see an x-intercept, that's what I was looking for. Second trace, 0 command. Left bound, right bound, guess. So about 3.73. Or negative 3.73.
That's the y-intercept.
The value for k.
Oh.
Which hopefully that's relatively close to where we thought, right? 4 -1 is a point. I would expect 4.2 to be the y coordinate to be relatively close to -1. I'd say that's pretty close. That feels pretty good. Yeah, go ahead, Lucia.
Why were you looking for x instead of y?
Because I used the x variable as k in my calculator, right? So I would, instead of writing k or y, I wrote x because my calculator can't graph functions of y, right? But it's just like a variable name, right? At this point, it's an equation with one variable. You call the variable whatever name you want. Brooks.
So when you did the guess function and you like put like or guessing between here and here, what was that finding? Was it finding the x-intercept or?
It's finding the solution to this equation.
Oh.
because I typed that equation equal to 0 in
Okay.
into y1. So wherever it crossed the x-axis was my solution.
Okay. Cool.
And I don't know any hope of solving a cubic trinomial where one of the terms is constant without a calculator. I don't know that there's hope to do that. Infeasible question for even like a graduate mathematics student. That's a potentially like incredibly difficult question that's probably not factorable. And nobody knows the cubic formula because it's like, like a half a sheet of paper long. And in fact, so for polynomials, we have like a general equation for linear, general equation for quadratic. You have a general equation for cubic, it's real nasty. You have a partial general solution for quartic, and then bigger than degree 4, there's no closed form formula possible. We've proven that for polynomial equations. So like these solving polynomials become really difficult problems very, very quickly. Particularly if you have irrational solutions. Yuck. Went okay? Brooks, you said you had some homework questions. I was just kind of stalling with this while you looked that up.
Yeah.
What do you got for us?
Might be easier, but just through my computer you can show you. Is that fine?
You just read me the problem.
Okay. It's
something.
just it has like problems split parts A to I, so that's the thing.
Just give me the setup and we'll go one part at a time.
Okay. Most of these were fine to do. It's about like velocity and stuff. The problem was like drawing the diagrams for it. So it was
So this is 3.7, right?
yeah, this is 3.7. It was number 2. Particle moving according to the laws of motion as equals ft, blah blah blah. And then it was find the velocity at time t, that was a, and then it was ft is equal to t cubed minus 12t squared plus 36t.
T cubed minus 12t squared minus 32.
36. Or plus 36 actually.
Plus 36. Is it t?
Yeah. Like this part was fine. It was just the diagrams part that came later that was difficult. But like you kind of have to do every other step.
Yeah. So like the idea here is it's the velocity diagram is what they're asking for.
Okay.
I think, right?
Yeah.
So you just be like, okay, when we do this, f prime of t is this thing. And we set this equal to 0. We can divide both sides by 3 and simplify this up a little bit. And then that it's like, okay, well that's this. So my places where we change velocity potentially are at like 2 and 6. I make like a sign diagram. Here's 2, here's 6. I pick a point, so like t equals 0, t equals 3, and t equals 7. T equals 0, I have negative times negative, so that's positive over there. At t equals 3, that's negative times positive, that's negative there. If t equals 7, I have positive times positive, so that's positive there, right?
Okay.
So like what I would just do is I would just be like, okay, my diagram is like up to here where at t equals 2, we're going forward and we change and go backwards up until like t equals 6 and we change and go forward again or something. That's like all I'm drawing.
Okay. And then the other one that said was that draw the diagram like figure?
I think that's probably what they wanted.
Oh yeah, and then you graph the position, velocity, and acceleration functions for zeros in between t and a.
So to do that, I would just use my calculator. So I'm going to do x cubed minus 12, minus 12x squared plus 36x. That's position. And then I'm going to graph the derivative of that. With respect to x. That's velocity. And I'm going to graph the derivative of that. Oops.
Do that.
Do y2 now.
Do we have to know how to do this on the test? Like, all of that in our calculator?
No, not necessarily. I mean, it should be doable even without the
Yeah,
calculator. I'm
it's like-
just,
Like, I don't know how to like get there, like, just pressing the button.
well, the ddx command is math and then ndrive. And then to get the y variables, you press vars. You go over to y vars, the y1, 2, 3, 4, all live under the function, which is the mode your calculator is going to be in for the entirety of this class. You'll never do parametric polar or whatever. So there's that. And then you said we're graphing it over some range of t's, right?
Yeah.
Like 0 to something.
0 to 8.
8. Okay.
Yeah.
That looks good. I'm just going to leave the y's where they are. That's probably fine. And I hit graph. So the y's probably need to be a little bit taller. That's fine. I can make those a little bit taller because 30 or something. Close enough. You get the idea at that point, right? And there's my, the blue is position, red is velocity, and the black is acceleration.
Why was position? Was that our original function? Or was that the derivative of the original function?
This is position.
Okay. I thought that. Wait, but didn't you take the derivative of whatever that first one was? The blue one.
So this is the velocity function that I use to draw my diagram because it's telling me whether I'm moving forward or backwards.
Yeah. Okay.
Mm-hmm.
We need to do that like for the velocity.
I don't
snake
think
diagram
you need to worry about it.
Okay, cool.
Yeah.
Thank you.
Is that okay with what we did there? And again, the calculator stuff is like only helpful if you have a calculator for that part, right? And I try not to ask you a whole lot of questions that are like, just do you know how to use the calculator? And then you'll get this question right or not. Try to have a very limited sample of those kinds of questions because, it's not asking you to do a whole lot of math. It's just use the calculator. Do you want to do any more of these? What do you guys think? Yeah?
Maybe some MCQs.
MCQs? Okay.
Oh, we're really big one, 62, but yeah, we did.
All right. We do 16. I'm going to switch back now to 8th hour. I should have done that earlier. Okay. That way I can actually, if I did them all in the wrong spot, who the heck knows anymore? I'm just going to scroll through.
We did do 16.
Okay, we did do 16. Should we do 26? Yeah, Sam.
We do an example for 10.
Like this guy right here. Sine inverse.
23.
That's 23. Okay. So first thing you'd have to remember is the derivative of sine inverse. 23. Is what we're doing.
1 over 1 minus, or square root of 1 minus x squared.
Yes. I believe that's right. Yes, that should be right. Okay, so ours then is the derivative of sine inverse 5x. So I'm just doing the chain rule. So I'd have a 5 on top and a 25x squared down there. So I think we want that guy.
Maybe, oh, okay.
Is that okay?
Yeah, I was just looking at the 5x, that wasn't, I didn't realize it's too complex.
So I was just, this is the general formula up top, right? And this is like a chain.
Oh, it's the channel.
Yeah.
Okay. That makes sense.
Does that feel okay? Cool.
So the one right above it should be pretty similar to that, right?
Yep. Except what's the formula difference between sine inverse and cosine inverse?
Negative.
Negative.
Sign.
That's it. So I'm going to have derivative of 2x, or derivative of x squared is 2x, and then a negative, and then I should have x to the 4th. So I want this one.
Would you mind doing this one out?
Oh, it's the derivative of the inverse of.
Yep. Our cosine is cosine inverse. And the derivative formula is the same as sine inverse, just with a negative. So okay. Just popped them in the same spots down here where I have the 5x's are just x squareds. Does that feel okay? Sure.
We need to memorize the inverse.
Absolutely, 100%. Yes, you'll see it in multiple places.
And is there any other ones we'll need to memorize?
Every derivative formula you've seen to this point. So you have, like the basic power rule, trigs, sine, cosine, tangent, cotangent, cosecant, secant. The inverse is sine inverse, cosine inverse, tan inverse, cosecant inverse, secant inverse, cotangent inverse, logs, exponentials. I remember that general inverse formula, right? Like g prime of x is equal to 1 over f prime of g of x. That's probably helpful. Yes, sir?
Just make sure an inverse of either, it was like a logarithm or natural log is just 1 over whatever it is, right? 1 over x.
The derivative of the natural log is 1 over x.
Yeah.
The derivative of log base b of x is 1 over x times 1 over natural log b. Just like the derivative of a to the x is a to the x times the natural log of a.
Oh, okay.
But yes, 100%. You got to have all those derivative rules memorized. What did I give you guys to help you do that? There's a Quizlet on My Notre Dame that has the derivative rules on it. I wrote them as best I could, but like they're not pretty looking because I couldn't figure out how to do like a LaTeX equation editor embedding into the Quizlet because it just doesn't seem like it's designed to do that. But I tried. I invested as much time as I was willing to try to get it, and then I gave up. Couple more? Yeah?
Yeah.
All right.
27?
27's a goof. Like, they just didn't do a good job. Like, for whatever reason, it didn't render the LaTeX code for, like, making these things pretty. So, like, don't even worry about it. Oh, let's see. Let's do this. 32 feels like a good one. let f be the function defined by f of x equals yada yada yada. Let g of x equal f inverse of x, where g of 3 is equal to 1. What is the value of g prime of 3? Meredith. Sure. What should I start by doing here? Or what's the key to knowing what to do first?
Their inverse.
Yeah. So as soon as I see that they're inverses, I know I can use that formula. Everybody agree? Okay. So g prime of 3 is what I care about, so that's going to be 1 over f of g of 3. And I know g of 3 is 1, so I just need to do 1 over f prime of 1. Everybody feel okay there? How do I find f prime? Yeah, and it's like one of the easiest derivatives you'll ever have to do, right? So f prime of 1 is going to be 3 plus 2 plus 1. Ta-da!
So if you're finding g prime of whatever number, you just put that number into g. But I should find that and then find f prime of whatever.
Yeah, because this function notation tells you to plug x
Okay.
into the same spot. G prime of 3 is 1. So turned out to be not so bad. One or two more. Nah.
Yeah, it could be like 62 then. Do we already do that one?
No, I did it with the other class though. It's okay. It's essentially the same as 61 was though. It's like the only thing that changed was like the numbers and the context. But like all the questions are asking to do the same thing, like, you know, approximate the second derivative, explain, and blah, blah, blah. You know, approximate the first derivative this time, explain in units. But here, the table is the function. Over here, the table was the first derivative. It's like the same problem, right? It's like, it's the same problem as before. But we can like, I don't know if I have the time on this. It's okay? Are you sure? Okay. Well, Lucia's spoken, so there it is. And we're gonna go 3.9. I'm so angry at myself for having done this. I'm gonna do it over here like a big old dummy. This is the one.
It's okay. At least we're getting like a virtual notebook.
It's the same old work will be there. All right. So we're gonna do one more example here. Because it established there's something that happens in this problem that is like really worth talking about and worth kind of seeing an example of. So we're into like the hardest level of difficulty for these related rates problems now, and these last three examples are kind of like as hard as you're gonna see. So it says car A is traveling west at 50 miles per hour, car B is traveling north at 60 miles per hour. Both are heading for the intersection of two roads. At what rate are the cars approaching each other when car A is 0.3 mile and car B is 0.4 mile from the intersection? You guys got a picture of kind of what's happening?
Yeah.
Okay.
Are they both meeting at the same time?
Well, they're heading towards it. Whether they get there at the same time or not, I don't know that it's
Are they heading away from each other?
No.
Towards.
Oh.
Both are headed for the intersection.
Oops. Try again. So that's west, right? And B is going north. Is everybody okay here? And probably to nobody's surprise, we're going to care about that as well. All right. Let's start naming some stuffs here, right? So what should I be naming things? What do you guys think? This is the hardest part, right? Is to like draw the picture and name the stuff. If you can get the stuff named, you're usually going to be all right. Here's what's confusing about this one. Okay, ready? I'm going to name those parts X, Y, and Z. Those are lengths, distances. Okay? Are those distances changing with respect to time?
Yeah.
Yes. Brooks, what's up?
Why would we care about the distance of Z if it's asking like the rate of both cars approaching each other? Is it because Z represents the distance between each other?
That's the distance between the two cars, right?
Yeah. Never mind.
That's okay. So those are all variables with respect to time, right? Okay. What then is the 50 miles per hour and the 60 miles per hour?
It's car A. It's 50.
But symbolically, what are we going to call those? Velocities, and a velocity is a type of, starts with an R, type of rate. And how do we write variables that are rates? With a derivative. So how would I write car A is traveling west at 50 miles per hour as a derivative? Good. So dx dt is going to equal, not quite.
Negative.
Why?
I'm looking at this.
It should be negative, but why is 50 miles per hour negative? It's a really important question. You'd think that. That's wrong.
It's because it's like, it's measuring, they're coming closer together, so it's like, it's distance minusing, distance decrease.
That is exactly right. So if we think about what is happening with x over time, it's getting shorter, correct? That means that if x is decreasing, its derivative must be negative. That's the way to think about it. Not which direction it's traveling. It's that the length of that side is decreasing with time. This is the part that's special about this problem that makes this worth doing an example of. Because it's the first time we've seen the positive or negative of the derivative hidden from you directly. Right? It's not giving you two words anywhere in this problem whether that derivative should be a negative or positive sign. It comes purely from thinking about what's happening with the picture. Sarah? Correct. So if they were heading away from each other, x would be getting longer, and y would be getting longer with time, so they would be positive, or they'd both be positive. Okay, the car B traveling north at 60 miles per hour. we should write that as dy dt, n equals negative 60 miles per hour. Good, for the same reason, right? And we're looking at what rate are the cars approaching each other when car A is 0.3 and car B is 0.4 from the intersection. What is that representing?
The distance between.
So rate. So what should we name that rate?
D.
dz dt. And we want that where x is equal to 0.3 and y is equal to 0.4. Does everybody feel okay? All right. So we've drawn the picture. We've understood the problem. We've denoted our variables and our quantities. Everybody feel good as to how we denoted everything and how we came up with everything? I'm going to tell you that picking up the derivative is negative because the length is, or whatever, is shrinking is a key skill for these related rates problems. That's why we're doing this particular example, is to illustrate that that skill is something that's going to come up in these high-level examples frequently. All right, what equation are we going to use to relate the variables in this problem together, x, y, and z?
Sine, cosine.
Pythagorean thing. Why wouldn't I want to use sine or cosine? We don't know anything about the angles involved, right? Okay. Now, if I take the derivative of this with respect to time, I'm going to get three derivatives back, right? dx dt, dy dt, dz dt. Is there any problem with that? Do I know all of those values for those derivatives, or at least have been asked to, like, that's the thing I'm supposed to solve for anyway? Yes, right? We have dx dt, dy dt, and we're asked about dz dt. Is there any need to eliminate a variable here? No, right? Because we want to know or do know about three derivatives. I have three variables in the equation. Everything should be good. Everybody's good with that? Again, that's the check that we didn't do when we had the cone problem previously, and we ended up having to go back and eliminate a variable. Because, Mr. Kulik, you didn't tell me that we need to check that before. And it's like, well, I need you to see what happens if you don't check. Because you're going to forget. You need to see what happens. So that maybe you're like, oh, no, it was one of those.
Why wouldn't you plug it in? You probably already just said this, but why wouldn't you plug it in instead of, why wouldn't you just plug it in to find Z instead of taking the derivatives and stuff?
You don't want Z. You want dz dt.
Oh.
And x and y aren't constants, right? They're variables. They're changing at every unit time, right?
Yeah.
Okay. Everybody feel good about how we differentiated? Let's plug them in. Uh-oh. What's Z?
We're trying to figure it out.
No, dz dt is what we're trying to figure out. We don't have Z. What was this, Myra?
Like the distance or whatever it's being written.
And the original equation being?
X.
Yeah, so at this instant, we know x is 0.3. and y is 0.4, and the Pythagorean theorem will hold, we have enough to find z, right? And now it's just question algebra again, right? So what do I have here? Let's see. dz dt is equal to -30, and then like, there's no good 5 in there. 48, so -78, I think is what that works out to. Mental math, I think. And this is miles per hour. Is anyone surprised that the value here is negative? No. Right? Why is it negative? The distance between the two cars is decreasing at every instant time, which makes sense, or at this particular instant of time. Right? What particular instant are we working at? The instant when x is 0.3 and y is 0.4.
If the distance was expanding, then the velocity or the acceleration was expanding.
Yes, if the two cars are moving away from each other, we'd expect dz dt to be positive in that instance. Does everybody feel okay here? This is the only example problem from 3.9 I wanted to do today. You guys still have your 3.9 papers that I gave you guys? If you didn't get some or you lost them, I have a stack over here. There's 3 papers. They're collated. I didn't have time to staple them, and I'm not going to staple them now because I feel like I've given them to everybody already. So if you need backups, you have to grab them. I think it goes up to 15 problems there. You guys can work on that some more. Or if you're like, I feel really underwater on test 3 and I want to do some more of that, you can do that. If you want to ask me questions about stuff, you can do that. I'm essentially going to stop talking here in this final 30 minutes of class. You can use to work on whatever you feel you need to most right now. So I'd love for you to do some 3.9 stuff, but if you're like, I need to do test 3 stuff right now, that is okay. But I do expect you to be working on something. So there's 3 pages in this book. So
Oh.
they're all in a row or whatever. I think.
Is 310 on the test?
Yes.
Does it go to 310?
The test?
Yeah.
3.9 is not on.
Oh.
So like, it's organized on here, where it's like, test 2, and then the next up is 3, 3, 4, 3, 5, 3, 6, 3, 7, 3, 10, test 4.
Okay, that makes sense.
So I try to keep it all like
Thank
the
you.
one note relatively organized, so it's like you can tell what's on what.
Okay. Thank you, I appreciate it.
Sure. Hi Sam, tell Coach Fox I said hi.
Good luck, Sam.
Bye-bye. At football practice.
Why are you leaving now?
They have like an indoor practice scheduled at some place off campus.
Yeah.
And I think it's
Oh, you
scheduled.
got your gum.
Keep it, it's okay.
Wow, look at the generosity.
Oh, he just wants me to throw away his gum.
Oh, well, that's less generous.